Imagine a state of matter that never stops moving, cycling through states without ever needing an energy boost. This isn't science fiction, it's the reality of time crystals, a revolutionary phase of matter that defies conventional understanding and holds immense promise for the future of technology. Time crystals represent a novel phase of matter, distinct from the familiar solids, liquids, gases, and plasmas. They exhibit periodic behavior in time, much like how atoms in a regular crystal are arranged periodically in space. This means their fundamental structure repeats not in physical dimensions, but across time. Unlike traditional crystals, which are defined by their spatial order, time crystals possess a unique temporal order. They constantly cycle between different quantum states, performing this oscillation indefinitely without consuming net energy. This remarkable property has led to comparisons with a perpetual motion machine, though it operates within the intricate rules of quantum mechanics. This fascinating behavior stems from their nature as a non-equilibrium phase of matter. Most systems in the universe tend towards thermal equilibrium, where energy is evenly distributed and motion ceases. Time crystals, however, maintain their dynamic state, perpetually oscillating without settling down. They are a testament to the surprising possibilities that emerge when quantum systems are driven out of equilibrium. The journey to realizing time crystals has been a captivating saga of theoretical brilliance and experimental ingenuity. It began with a bold theoretical proposal that challenged long-held assumptions in physics, followed by years of skepticism and ultimately triumphant experimental validation. The concept of time crystals was first introduced in 2012 by Nobel laureate Frank Wilczek, a renowned theoretical physicist. Wilczek, known for his work on asymptotic freedom in quantum chromodynamics, extended the idea of spontaneous symmetry breaking from space to time. He theorized that, just as spatial crystals spontaneously break translational symmetry in space, a quantum system could spontaneously break time translation symmetry. This meant a system could exhibit periodicity in time, switching between quantum states at regular intervals indefinitely. Wilczek envisioned a system that would oscillate at a frequency different from any external driving force, or even without one, much like a pendulum that keeps swinging without being pushed. This was a radical departure from the conventional understanding that systems in their lowest energy state, ground state, should be static. Wilczek's initial proposal, particularly for a continuous time crystal in a ground state, faced significant skepticism within the physics community. Many physicists argued that such a phenomenon was impossible, citing fundamental principles like the second law of thermodynamics and the nature of ground states. A key argument against them was a no-go theorem, which suggested that a system in its lowest energy state could not spontaneously exhibit dynamic behavior. The core of the challenge lay in reconciling the idea of perpetual motion with the laws of physics. If a system were truly in its ground state, it should be static and unchanging. Any observed motion would imply energy consumption or an external energy source. This apparent contradiction fueled intense debate and pushed researchers to refine the theoretical framework, leading to the crucial distinction of discrete time crystals operating in non-equilibrium conditions. The breakthrough came not with continuous time crystals in equilibrium, but with discrete time crystals in periodically driven non-equilibrium systems. These systems are constantly kicked by an external force, but they respond at a subharmonic frequency, oscillating at a period that is a multiple of the driving period. This unique response is the hallmark of a discrete time crystal. In 2016, the first experimental observations of discrete time crystals were independently reported by two separate research groups. One team, led by Christopher Monroe at the University of Maryland, used a chain of trapped ytterbium ions. The other, led by Mikhail Lukin at Harvard University, employed a dense ensemble of nitrogen vacancy centers in diamond. Both experiments demonstrated the characteristic subharmonic oscillations, confirming the existence of this exotic phase of matter. These initial discoveries opened the floodgates for further exploration and validation. The field rapidly advanced, with significant milestones achieved in subsequent years. In 2021, a landmark announcement came from researchers at Google in collaboration with physicists from Stanford, Princeton, and other universities. They successfully created a genuine time crystal using Google's Sycamore quantum computer. This was a pivotal moment because it demonstrated the robustness and scalability of time crystals in a programmable quantum system. The Google team showed that their time crystal could maintain its periodic behavior for an extended duration, a crucial step towards practical applications. Around the same time, another research group reported creating a time crystal in a diamond, further validating the phenomenon across different material platforms. This diversity in experimental setups underscored the universality of time crystal physics. These experiments often involved manipulating the spins of electrons or atomic nuclei, using precise laser pulses or microwave fields to drive the system out of equilibrium. The exploration continued into more exotic quantum systems. In 2022, scientists achieved another significant feat by connecting two time crystals in a superfluid of helium-3. Superfluids are quantum fluids with zero viscosity, allowing for unique quantum phenomena. Connecting time crystals in such a medium was a potential step toward a new kind of quantum computer, where the interactions between these temporal structures could be harnessed for the computation. This experiment highlighted the potential for time crystals to interact and form more complex quantum architectures. The year 2024 brought further advancements, showcasing the practical utility of time crystals. Researchers from the University of Chinese Academy of Sciences, UKS, demonstrated the use of a time crystal to enhance the stability of quantum states in a quantum computer. This was a direct application of time crystal properties to address one of the most pressing challenges in quantum computing: decoherence. By using the time crystal's inherent stability, they could protect fragile qubits from environmental noise, a critical step towards fault-tolerant quantum computation. Also in 2024, a team from TU Dortmund University achieved a remarkable breakthrough by creating a highly durable time crystal with a lifespan millions of times longer than previously achieved. This was accomplished by carefully engineering the system to minimize energy dissipation and maximize the coherence time of the time crystal. The increased durability is paramount for any practical application, as it allows for longer computation times and more reliable operations. These continuous advancements underscore the rapid progress and immense potential of time crystal research. The unique properties of time crystals make them incredibly appealing for the burgeoning field of quantum computing. Their inherent stability and periodic nature offer solutions to some of the most formidable challenges faced by current quantum technologies. For tech enthusiasts, understanding these applications reveals a glimpse into the next generation of computational power. Time crystals possess unique properties that may be profoundly useful for building better qubits, the fundamental building blocks of quantum computers. Qubits, unlike classical bits, can exist in a superposition of states, both 0 and 1, simultaneously, and exhibit entanglement, allowing for exponential computational power. However, qubits are notoriously fragile. They are highly susceptible to environmental disturbances, a phenomenon known as decoherence, which causes them to lose their quantum information. This is where time crystals shine. Their inherent temporal order and robustness against perturbations make them ideal candidates for enhancing qubit stability. Time crystals can be used as a control mechanism to protect the fragile quantum states of qubits from disturbances. By coupling qubits to a time crystal, or by using the principles of time crystals to design more resilient qubits, Researchers aim to create quantum systems that can maintain their coherence for much longer periods. This enhanced stability is critical for performing complex quantum algorithms and achieving fault-tolerant quantum computation. Beyond active computation, time crystals may also serve as a revolutionary form of quantum computer memory. Current quantum memories are often limited by their short coherence times, meaning they can only store quantum information for fleeting moments. The perpetual, stable oscillations of a time crystal offer a compelling solution to this problem. Imagine a memory unit that inherently resists decay and maintains its state over extended periods. Time crystals, with their robust temporal periodicity, could provide a stable platform for storing quantum information. This could involve encoding quantum data within the oscillating states of a time crystal, or using its properties to stabilize other quantum memory elements. Such a breakthrough would enable larger-scale quantum computers and facilitate the development of quantum networks. One of the most profound implications of time crystals for quantum computing lies in their ability to seemingly negate the effects of entropy, which is the tendency for systems to become more disordered over time. In classical physics, isolated systems inevitably move towards a state of maximum entropy, where information is lost and order dissipates. Quantum systems are also prone to this, with decoherence being a manifestation of increasing entropy. Time crystals, however, operate under a quantum mechanical principle known as many-body localization, MBL. In a many-body localized system, interactions between particles are restricted, preventing the system from thermalizing and reaching a state of equilibrium. This means that a change affecting one part of the time crystal remains localized and doesn't cause chaos or spread disorder throughout the entire system. This localization prevents the system from heating up and losing its quantum information. For quantum computing, MBL offers a pathway to build systems that are inherently resistant to thermalization and decoherence, allowing for more stable and reliable quantum operations. Quantum computers based on time crystals could lead to breakthroughs in various fields, making previously impossible scientific applications a reality. The enhanced stability and coherence offered by time crystals would unlock new frontiers in drug discovery, allowing for the simulation of complex molecular interactions with unprecedented accuracy. This could accelerate the development of new medicines and therapies. In materials science, time crystal-enhanced quantum computers could design novel materials with tailored properties, leading to advancements in superconductors, catalysts, and energy storage solutions. Financial modeling could become more sophisticated, enabling better risk assessment and optimization strategies. Furthermore, the ability to perform complex simulations could revolutionize artificial intelligence, leading to more powerful machine learning algorithms and truly intelligent systems. The integration of time crystals into quantum computing architectures represents a significant leap forward, promising to reshape our technological landscape and solve some of humanity's most pressing challenges. The world of time crystals and quantum computing is evolving at an astonishing pace, pushing the boundaries of what we thought possible. If you're fascinated by cutting-edge technology and the future of computation, now is the time to dive deeper. Explore the latest research papers, follow leading quantum labs, and engage with the vibrant community of quantum enthusiasts. Your curiosity could be the spark that ignites the next great discovery. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.